Okay. So up until this point, we've been talking about simplifying. And last time we had kind of finished completing all the procedures that we need to transfer back and forth between these three forms of quadratics, right? Last time we had finished doing all of our factoring shortcuts that we needed. So now we had like a fully functional procedure on how to move back and forth between all these different forms. Okay? Today, we're going to start talking about solving. And, hello. Thanks. Sergio, you know what was coming.
No, it's not Corona. Don't worry, it's my counselor. I know you guys got excited for a second.
I think that's not for right now, though, Sergio, if you look at it. I think it's for 12:15.
Yeah, it's 12:15.
Yeah, so you're only going to be 55 minutes early. But all right. So we're going to go through a bunch of different techniques we can use for solving, because depending on the form that our quadratics in, we would want to take a different approach. Okay with that idea? So the first situation we'll talk about is if we have something that's in intercept form. So the key in intercept form is using the zero product property, which states that if you have two things that multiply to give you 0, one or both of those things must be 0. Critically important. It's not true like if the two things multiply to give you 1, you can't just set each of them equal to 1. Because how many different numbers multiply to give you 1? Infinitely many. So you'd have like 1 and 1, 2 and a half, 3 and a third, 4 and a quarter, 5 and a fifth, not counting even the negatives. We have like an infinite number of those. Now to multiply to give you 0, the only way that happens is if one or both of those two numbers is 0, right? Amy? If and only if. You're welcome. So, for example, let's say we have something like this. Well, by applying the zero product property, I can take each of these factors and set them equal to 0 and solve each one of them independently. Okay with that idea? Now, keep in mind, I can also many times take a standard form equation and turn it into an intercept form equation, which makes some of these standard form equations solvable. So for example, if I have x squared plus 3x minus 10 equal to 0, I can try to turn that into an intercept form equation. How do I do that? Yeah, so you can factor it using the shortcut like from last class. What is the shortcut? How does this one factor? -2 and +5, right? Those are the two things that multiply to give me -10 and add to give me +3. So then I can set each of these factors equal to 0 using the zero product property and solve each of them independently. Does this mean we can solve all standard form equations this way? No, why not?
It's x is x squared. Wait, no, I don't know. But yeah, doesn't x squared have to be 1 or no?
No, we can still factor things when the x squared isn't 1. We can't use that particular shortcut, but we can still factor things like that. Tommy? Well, if it doesn't equal 0, we can just make it equal 0 by like adding or subtracting things from both sides, right? Is every standard form quadratic factorable using our methods? No. And that's the wrinkle, right? So this, what we've done here, doesn't work all the time because not everything is factorable using the methods that we have available to us. I mean, everything is factorable, but not conveniently so to where we can use one of our methods that we've developed so far. So we'll have to circle back to that because we don't have all the standard form stuff being able to be solved. If we have a vertex form problem, we're just going to use the reverse order of operations. So let's say we have a vertex form problem that looks like this. When we say order of operations, when we are solving, we start at this end and work backwards. When we're simplifying, we start with parentheses and work that way, right? So what's the first thing that we would need to undo in this problem? Well, I'd want to undo the addition and subtraction. So I see I have a +5 and I see a -8. Now I notice that the +5 is inside a set of parentheses. So I really can't undo that +5 until I've cleared all the parentheses and stuff out of there. So I can't deal with that right now. But I can deal with the -8. So to undo that -8, we'll just add 8 from both sides. The next thing I would need to do is undo any multiplication or division. Well, I see that I really have a ×2 there. We don't really write the multiplication symbol, but I know it's there. So to undo that ×2, we'll just divide both sides by 2. Okay with that. The next thing we need to do is undo any exponents. So I have a squared there. I need to cancel that out. How do I cancel out a squared? A square root. So I'll do the square root of both sides. I'm going to pause here and do a little aside because we need to talk about some properties of roots that maybe you've seen before and need a little refresher on, or maybe you haven't seen before. So the first thing is if we square root both sides of an equation, it's going to create a plus or minus. The next thing is that the square root of a product is equal to the product of the square roots. Similarly, the square root of a quotient is equal to the quotient of the square roots. And the last thing is that the square root of a sum or difference is not equal to the sum or difference of the square roots. So those are 4 little asides that we need to make sure that we remember. And some of these are things that maybe you saw before in your Algebra 1 class, or you saw in geometry, or you picked up somewhere along the way. And some of these things are like, oh, I don't know that I've ever been told that. Maybe you haven't, or maybe you have and you just forgot it. You know, like stuff happens. It's been a long time. I forget stuff. Okay. So the square root of x plus 5 squared, the square cancels the square root. So I'm just left with the x plus 5. Because we square rooted both sides of the equation, we get the plus or minus. And the square root of 4 is just 2. So far, so good? Okay. So the next thing I would need to do then is to subtract 5 from both sides. Now I can't subtract 5 from a plus or minus 2 because there's really 2 operations there. But I can certainly evaluate that just by separating the plus or minus 2 into 2 statements. So negative 5 plus 2 is negative 3, and negative 5 minus 2 is negative 7. So those would be my 2 solutions. Now it's worth pointing out here that there are some vertex form equations that could also be thought of as standard form equations, right? So for example, let's say I have 3x squared plus 3 equals 28. This is still vertex form. Why is that? I could think about it that way, right? Everybody agree? So it's still vertex form, but it could also be thought of as standard form too, right? Everybody agree with that? So you could think of it as either one. So since we can still think of this as vertex form, we could solve this problem using the reverse order of operations. So subtract 3 from both sides, and then divide both sides by 3. And then we'll square root both sides. Because we square rooted both sides, we're going to get a plus or minus. Because we're square rooting a fraction, we're going to get the square root of the top over the square root of the bottom. Now, hopefully you recognize the square root of 25 is just 5. So we're left with plus or minus 5 over the square root of 3. Do you guys remember encountering situations similar looking to this in geometry last year? Because we didn't like to leave the square root in the denominator of a fraction, right? Do you remember how we remedied that situation? Well, we can just multiply the top and bottom by the square root of 3. All we're doing there really is multiplying by 1, right? So that's fine. It's okay to do that. When I multiply something in a square root with something not in a square root, they don't multiply together, so we just write them next to each other. And the square root of 3 times the square root of 3 is the square root of 9. But the square root of 9 we can actually evaluate. That's just 3. Are we okay there? So some standard form equations, or standard form quadratics like this one, that are really the same as vertex form quadratics, we can just apply the reverse order operations to them directly, right? But what if we have a standard form quadratic like this? Can I apply the reverse order of operations to this currently, as it's currently written? No, right? Because I have both x's and x squareds. So I can't think of this as a vertex form problem simply. Could I factor this? Are there two numbers that multiply to give me -2 and add to give me 5? Not integers anyways, right? So what am I going to do here? Well, I have a standard form equation. I can convert that into a vertex form equation using completing the square. And once I have it in vertex form, I can use the reverse order of operations to solve it, right? So let's do that. So the first thing I would need to do is make sure the leading coefficient is 1. Already is 1, so no problem there. And then we're going to add b over 2 squared and then subtract b over 2 squared. Right together like that. Everybody remember doing this? Completing the square process? So we'll take these first 3 terms and we can factor this. So this is always going to factor as x plus b over 2 and then quantity squared. And then I'll worry about combining the like terms of the stuff on the outside. So 5 over 2 squared is 5 squared over 2 squared. And then to be able to combine 2 with 25 over 4, I need to have a common denominator. That common denominator would be 4. So the 2 just becomes 8 over 4. And now, since they have a common denominator, I could combine those like terms to make -33 over 4. Notice here we're now in vertex form. Now that we're in vertex form, we can use the reverse order of operations to deal with this. So we'll add 33 over 4 to both sides. Next, we would look for something to undo multiplication or division wise, but there's none of that. So we'll go and get rid of the exponent next then. So we'll square root both sides. Because we square root both sides, it creates a plus or minus. Because we're square rooting a fraction, we'll have the square root of the numerator over the square root of the denominator. The square root of 4 is just 2. And then we'll subtract 5 over 2 from both sides. Now I can't combine something in a square root with something not in a square root, but they do have a common denominator, so I could write this all as a single fraction, like that. And there we go. And we've just done something really important here. So notice what we did is we went from standard form to vertex form using completing the square. We can always do this. Always possible to do that. We can go from vertex form to a solution using the reverse order of operations. Can always do that. So what we know then is that we're always going to be able to solve a standard form quadratic regardless of what it looks like, right? Everybody okay with that? So as long as we can get our quadratic into standard form, doing some kind of rearranging, we'd then be able to solve it because we can just do completing the square and reverse order of operations. It gets better than that though. The steps for completing the square are always the same, right? The steps for the reverse order of operations are always the same. So, if I take a general standard form quadratic, I should be able to create a formula to take me straight to the solution by performing completing the square and then the reverse order of operations on just a very general setting. So let's do that. So let's say we have the standard form quadratic ax squared plus bx plus c. That's as general as we can make it, right? A, b, and c can just be whatever they want. So as long as a is not 0, right? Because if a is 0, it's not quadratic anymore. But other than that, those numbers could be whatever they want. Everybody's okay with that idea? Okay, so now what we'll do is we'll do our completing the square and our reverse order of operations. And when we're done, we're going to be left with a formula to find x. That'll be written in terms of a, b, and c. So we can just read those values off of our problem and plug them into our formula and spit out an answer. Sound good to you guys? Okay. This process that we're about to do is not trivial. It's not something I would ever ask you to repeat. So if you just want to sit and watch, you're welcome to do that. It's going to be a little bit yucky looking, but it's not like impossible to follow. But I'm just letting you know right now that it is what we're about to do takes a little bit of time. It gets a little bit alphabet soupy, but it's not something I'd ever ask you to be able to repeat. But I think it's important that you see that the way we're going to generate this formula is just the same thing as doing these two processes that we're familiar with. Okay? So to complete the square, we need to make sure the leading coefficient is 1. So I'm going to start by factoring out an a. So far, so good. All right. Then I'm going to add and subtract b divided by 2 squared. So our b in this case is really like b over a. So b over a divided by 2 is b over 2a. Everybody so far so good? And then we distribute the a to those last two pieces to kick them out of the parenthesis. And I just turn that back into a c because a times c over a is just c, right? Okay. So that x squared plus b over ax plus b over 2a squared factors, it's always going to factor the same way, into x plus b over 2 squared. Okay with that. So we're basically done with the completing the square part. Let's go ahead and multiply some of this stuff out and make some common denominators and start doing the reverse order of operations. So b over 2a squared is just b squared over 2a squared. 2a times 2a is 4a squared. So when I multiply these together, I'm going to have an a cancel from the numerator and an a cancel from the denominator. So to make a common denominator with c, I need to multiply the top and bottom of that by 4a. And now I'm going to move that stuff outside of the parentheses over to the other side. So I'm going to add over b squared over 4a and subtract over 4ac over 4a. But since they have a common denominator, I'm going to write them as a single fraction. So far, so good. We'll divide both sides by a, or really the way I think about this is just multiplying by the reciprocal. Since there's fractions involved, it's a little bit easier to think about that as a multiplication problem than a division problem. So a times 4a is 4a squared. And then we'll square root both sides. In case you haven't noticed, we finished completing the square and we're on to solving, right? We started doing that a minute ago. So I get a plus or minus, and then since I'm square rooting a fraction, that's the same as the square root of the numerator over the square root of the denominator. Notice that the square root of 4a is something that I can do. The multiplication problem, I can just think about that as the square root of 4, which is 2, times the square root of a squared, which is just a. I can't do the same thing in the numerator because it's a subtraction problem, right? We can't break up a square root with a subtraction in it. So we're just stuck with that the way it is up there. That's fine. And my last step then is to subtract this b over 2a to the other side. Notice that I have a common denominator, so I'm just going to write this all as a single fraction. And what I'm left with then is this formula. How many of you guys recognize this? I'm guessing a handful of you would. This is called the quadratic formula. Yeah. Which says for ax squared plus bx plus c equal to 0, x is equal to negative b plus or minus b squared minus 4ac all over 2 times a. So this is the result that we wanted. So for example, if we went back to this problem that we did a moment ago, to solve this problem we had to do completing the square and then the reverse order of operations, right? Alternatively, I can just identify the values for a, b, and c and then plug them into the quadratic formula. Five squared is 25. 4 times 1 times 2 is negative 8. 25 plus negative 8 is positive 33 over 2. It's pretty gnarly, Sergio. Well, there'll probably be questions I tell you to do, questions I tell you to just do whatever way is easiest for you. Because it is important that you're able to do most of these ways, because we have because it's easier or faster a lot of times to deal with. So in intercept form, we can use the zero product property, or we can take our intercept form to standard form and then use the quadratic formula to get our solution. In standard form, we can factor sometimes. We could use the reverse order of operations, again, sometimes, but we can always use the quadratic formula. That always works. In vertex form, we can use the reverse order of operations always, or take vertex form, turn it into standard form, and then use a standard form method to get your solution, depending on what that standard form looks like. Maybe it's factorable, maybe it's not. You could always use the quadratic formula there because it's a standard form, but the advantage here on these ones that don't always work is most of the time they're faster than the quadratic formula would be. Particularly if there's a factoring shortcut, you can do that almost like in 10 seconds if you see the shortcut right away. I would wager it would take you longer to grind through the arithmetic and the quadratic formula to get your two answers than that. Sergio.
So the quadratic formula, if we follow the entire thing from calculating backwards.
Yes, but we'll come back to that in a few minutes. Well, next time, I should say. Yes.
What does it say under SF?
Just method. Yeah. So some standard form method, whatever one you feel like doing or works in that situation. There is still one situation that I've been cleverly avoiding that we can run into that when solving these quadratics, it still needs to be addressed. What if we have this? Something like this. X squared plus 1 is equal. What's going to be the easiest way to solve something like this? Yeah, I would just use the reverse order of operations. So we'll subtract 1 from both sides. And then we'll square root both sides. So we have plus or minus the square root of negative 1. Does anybody see a problem with that? We can't square root a negative, right? At least the result, we should say this. The result of the square root of a negative is not a real number. That we can say. Well, this has happened to us a bunch of times in our mathematics education before this. If you go back to elementary school and you started doing subtraction, eventually you wanted to do something like 3 minus 4, and you have a number that for 3 minus 4. What did you do? No, eventually you...
eventually you learn that there's a way that you can do it.
By
learning that there's negative numbers.
Inventing negative numbers, right? They hadn't existed to that point, but you extended your definition of what a number was to include these negative things so that you could do that problem. A few grades later, you started doing division. Eventually, you ran into something like 3 divided by 4. What happened? You added fractions or decimals so that you could do that kind of a problem, right? Probably into middle school or high school, you ran into things like the square root of 2 that couldn't be written as a fraction. So you added some more numbers, these things that can't be written as fractions, like pi or the square root of 2. We're going to do the same thing now. We're going to extend our set of numbers again so that we can do a problem like this. Now, this seems artificial, but we've done it 3 times already in your mathematics education. It shouldn't feel that weird to do it. It's just been a little while since we've done it. So we're going to complex numbers. So the complex numbers are of the form a plus bi, where a and b are real numbers, and I is equal to the square root of negative 1. So we're going to call imaginary number. So let's do a couple of examples. We'll just decide if something is a complex number, and if it is, we'll identify its values for a and b. Sound good? Just to make sure we understand the definition. Five plus 6i. Is that a complex number? Yeah. What's 5? The value for b is 6. No big deal. How about 7 minus 2i? Is that a complex number? Yeah. What's the value for a? What's the value for negative 2? Everybody okay there? How about 3 plus 5i all over 4? Is that a complex number? Well, sure it is. We can just write it as 3 over 4 plus 5 over 4i. Right? If I do that, that's still the same thing. So sure, that's a complex number. Everybody okay with that idea? Huh? It's the same thing as writing it next to it, right? Isn't 1/2 times 3 the same as 3/2? Same thing still. You could put it in the numerator also. That would be fine. What about -2i? Is that a complex number? Sure it is, right? That's the same thing as 0 minus 2i. So the a is 0 and the b is -2. Everybody okay there? How about 8? Is that a complex number? Sure it is. 8 plus 0i. So sure, that's a complex number. What's the takeaway here? They're all complex numbers, right? Everything is a complex number, which is what it should happen, right? When you added in the negatives, you created the integers that included everything you had before and then these new negative numbers. You don't want to create a new set of numbers where you lose stuff that you had before. You need to have everything you had before and then some extras, right? So that's all we've done here. We still have all the real numbers. We just also have these parts that have imaginary pieces to it. Okay with that idea? Okay. So now that we have a reasonable understanding of what it means to be a complex number, we need to talk about operations. How do we add, subtract, multiply, and divide these things? Before we go back and start using them in a solving problem. So we'll do that first, and then we'll circle back and add this into solving, go back to solving quadratics here after we've talked about how to deal with these complex numbers, okay? So let's say we want to do 5 plus 2i plus 6 minus 7i, right? That's just a sum of two complex numbers. Everybody agree with that? So what are we going to do here? Well, we're basically just combining like terms. So we'll add the real parts together. 5 plus 6 is 11. And then we'll add the imaginary parts together. 2 plus a -7 is -5i. Everybody okay with that idea? That works exactly as we'd hope it would, right? Nice and simple. Subtraction. So let's say we were to subtract these two numbers. What's the one thing we have to be a little bit careful about here? Well, I have to make sure I'm distributing that negative, right? So really this is -6 plus 7i. So 5 -6 is -1. 2 then is +9. But again, not really that difficult, right? Basically, all we're doing is combining like terms again, which is not so bad. Next, let's talk about multiplication. Let's say we have something like 6 times 7i, or 7 plus 2i. What do you think we should do here? Just distribute. Yeah, exactly right. Exactly as you'd expect. So I just get 42 plus 12i. No big deal. What if instead I had 6i times 7 plus 2i? Well, same thing. We'll just distribute. So that gives me 42i plus 12i squared. Uh-oh. What the heck does I squared mean? So if I is equal to the square root of -1, if I square both sides of that, I'd have this, right? The squared cancels the square root, so I squared should just be -1. Everybody buy that? Okay, so all we'll do is we're going to replace that I squared with a -1. So really I have -12 plus 42i. Everybody okay there? No big deal though, right? Still basically exactly as we'd expect. We have this little extra piece to deal with. What the heck does I squared mean? But it's just a substitution. I squared is -1. No big deal. More multiplication example. What if I have something like 3 minus 2i times 5 plus 6i? What do you think I should do here? FOIL. Yeah, exactly as you'd expect, right? So I get 15 plus 18i minus 12i squared. Well, 18i minus 10i is just 8i. And we know that I squared is the same as -1. So -12 times -1 is +12. So I really have 27 plus 8i. We okay there? Next up is division. One of these division situations we've already seen. So if I have something like 3 plus 6i divided by 2, I can just break it up and reduce the fractions individually if possible. Right? That's no big deal. Pretty easy to deal with that. But what if it was 2i in the denominator, not just 2? Can I do the same trick? Well, I can, but it's not going to help me any. Why is it not going to help? Think back to our definition of a complex number. Where's the I located? In the numerator or the denominator? It's in the numerator, right? So for us to make this a complex number, somehow that I in the denominator has to get out of there. So how are we going to do that? Not multiplying by 2. Let's multiply by I. Why would we want to do that? It makes an I squared in the denominator, which is just -2. Or negative I, or negative, you know what I meant. We're going to get a -2 in the denominator. So I distribute the I in the numerator, and then I just multiply the I into the denominator. And we know that I squared is -1. So I'm going to have 3i over -2 plus -6 over -2. Or I can just think about this 3 minus 3 over 2i. Everybody okay there? Still no big deal, right? There's one little trick, but it's an easy trick to remember. We just need to multiply top and bottom by I, and then that does it. Gets rid of my I in the denominator, and then I just simplify, and it's, basically turns into a problem like we did before that was no big deal. Last one. What if the denominator is 2 minus 3i? Can I do the same trick and just multiply the top and bottom by I? No, because when I distribute the I, we'll have 2i minus 3i squared. I still have an I there, right? So what's the trick? There's got to be a trick, Mr. Kulik. Here's the trick. I'm going to multiply the top and bottom by 2 plus 3i. Is called a conjugate, is the name for that sort of thing, when it's the same binomial, just with the opposite sign in the middle. Notice that that 2 plus 3i is identical to the denominator of my problem, except for the sign in the middle is changed. Everybody okay with that? So that's the trick. So now we just FOIL out the numerator and denominator. So I get 6 plus 9i plus 12i plus 18i squared. And then I get 4 minus 6i plus 6i minus 9i squared. Everybody okay with that? Well, 9i and 12i is 21i, and I squared is negative 1. Negative 6i and positive 6i just cancel out, and I squared 1. So I have 6 minus 18, so negative 12, plus 21i. And I have 4 minus a negative 9, so that's 13. And then I just separate this into two fractions. We okay there? Okay. So again, it just basically boils down to a FOIL problem after you remember the trick, right? And the trick is just multiplying by the conjugate. It's a good trick to remember. It comes up a couple of times in this course. The last situation that we want to talk about is the absolute value. So before we do that, remember what the definition of the absolute value is for real numbers? It was the distance on the number line from that number to 0, right? Okay, well, let's try to use the same definition for complex numbers. So which complex? 3 plus 2i or 2 plus 3i? If I was going to put them on a number line, which one would come first? It doesn't really make sense, right? And that's because there's two components to this. There's a real part and there's an imaginary part. So if we really want to describe the relationship here, we need to use a two-dimensional representation. Rather than a one-dimensional on a number line, we have to graph this on a plane, a two-dimensional. So the way we do this is we have like a real axis and an imaginary axis. So for 3, 2, we go 3 over and 2 up. And for 2, 3, we go 2 over and 3 up. Everybody okay with that notion? So instead of using a number line, we're going to use a plane. That's fine. So for complex numbers, the absolute value is going to be the distance on the plane from that point back to what location do you think is going to substitute as 0? The origin, exactly right. So for example here, this distance is going to represent the absolute value. So how do I compute that distance? Think about this. This is a right triangle where I went 2 over and 3 up, right? What's going to be the easiest way to solve for the hypotenuse of that right triangle? Geometry, kids? No, it's the one thing from geometry that everybody remembers. Maya. Exactly right, the Pythagorean theorem. So, what this basically boils down to, come on, is that the absolute value of a complex number is just the square root of a squared plus b squared. Oops. So for example, if I wanted to find the absolute value of 3 minus 4i, it's just fine. You okay there? So it just boils down to a formula. There's nothing more complicated to do it. You can do every one the exact same way. Keep in mind, are you always going to get a whole number out of this? No, most of the times you get it like something with a square root still in it, which is fine. No big deal. Okay. Back to solving now, Sergio. I mean, if it's time to go, you can go.
Well, I don't go, I'm not and then if I do go, I so it's not okay. Thank you.
You're welcome. So let's say we want to solve x squared plus 3x plus 1 equals 0. Can we factor this? Two things that multiply to give us 1 and add to give us 3? No, right? Hold on one second. Hold on, I got to think. Let's do that. Sorry, let's just make it 1. The other one wasn't going to work out the way I wanted it to. So in this case, since it's not factorable, I need to use the quadratic formula. So a is 1, b is 1, c is 1. That's pretty easy. So 1 squared is just 1. 1 times 4 times 1 is 4 over 2. And 4 minus 1 is negative 3. And now we've run into these situations where we have a negative under our square root, right? And this was a situation that we were stuck at before, but we can deal with this now. So the square root of negative is the same thing as negative 1 times 3, right? And I can make that the square root of negative 1 times the square root of 3, right? Everybody agree there? And the square root of negative 1 is just I. So basically what it comes down to is the negative sign underneath the radical just turns into an I outside the radical. Everybody okay with that? Done. Let's do one more and we'll stop. Sound good? Yay! I thought so too. I'm exhausted. Say we have 4x squared plus 32 is equal to 0. What do you want to do first? Or how do you want to solve this one? I would do the reverse order of operations on this. You could still use the quadratic formula, but I think the reverse order of operations will be a little bit quicker and a little bit more straightforward. Everybody okay with that? Okay. So we'll just start by subtracting 32. And then we'll divide by 4. Somebody is popular today. So that gives me x squared equals negative 8. And we'll square root both sides. So the square root, when we do that to both sides, creates a plus or minus. We have a negative, so that's going to create an I outside the radical. And then the square root of 8. Can I do better than that? Remember that 8 is equal to 4 times 2, right? So the square root of 8 has to equal the square root of 4 times 2, or the square root of 4 times the square root of 2. So I can really think about this as 2i square root 2. And that's going to be my best version. Where that square root of 4 becomes that 2. Right? We okay there? Cool. We're stopping.